In this video, we're beginning our discussion of Chapter 21, where we cover electrochemistry. This is a broadly important subject that affects energy storage. It's important for biochemical systems and for measurement science. And we'll start off our discussion in this video thinking back to what we learned in Chapter 4 of General Chemistry 1 on redox reactions. We'll look at balancing, and then we'll use these redox principles to build electrochemical cells. We'll look at both voltaic, or what are sometimes called galvanic cells, and electrolytic cells. Then we'll look at cell potential. Refreshing what you know about redox reactions from General Chemistry 1, we know that whenever we have a redox reaction, electrons are transferred from one chemical species to another. The oxidation process is the loss of electrons. The reduction is the gain of electrons. These occur together. So, oxidation increases the oxidation number of a particular species, and reduction decreases the oxidation number of a species. If you don't remember oxidation numbers, you might want to go back to Chapter 4 and refresh your memory on how oxidation numbers are assigned. The oxidizing agent in a reaction is the species that takes electrons from a substance that is being oxidized. The oxidizing agent itself is reduced. The reducing agent is the species that gives electrons to the substance that is being reduced. Therefore, the reducing agent is the species that is oxidized. And in all our reactions, we see that the number of electrons that are gained by the oxidizing agent will equal the number of electrons lost by the reducing agent. Here's a summary of our redox terminology using a reaction we've looked at previously as an example. So we're taking zinc metal and we're putting it in an acid, for example, hydrochloric acid. And when we do that, we find that the zinc dissolves up and becomes zinc ion in the aqueous solution, and hydrogen gas is released. For our oxidation process, we know that one reactant is losing electrons, and in this case, that's zinc. Zinc is losing 2 electrons. The reducing agent is oxidized. Zinc here is the reducing agent. Zinc is the reducing agent, and it is oxidized from the 0 to the +2 state. So its oxidation number is increasing. The reduction part of this reaction is the other reactant that is gaining the electrons. So in this case, that's the hydrogen ion, which gains the electrons. The oxidizing agent itself, which is the acid. Acids are very commonly oxidizing agents. The oxidizing agent itself is reduced. Hydrogen ion is the oxidizing agent and becomes reduced to hydrogen gas, and its oxidation number decreases from +1 to 0. When we have a redox reaction, we can't balance it simply by inspection in all cases. In some cases, we'll find that charge won't balance out when we do that. So we have something called the half reaction method for balancing redox reactions. This allows us to account for atom balance as well as charge balance, and it also allows us to vary from acidic to basic media. So this is a refresher on what you covered in General Chemistry 1, but we'll go through this and look at one example. First, when we want to do a half reaction balancing, we divide the reaction into half reactions. Each contains oxidized and reduced forms of one particular chemical species. So we'll have an oxidation half reaction and a reduction half reaction. Next, we balance the atoms and the charges in each half reaction. First, we balance the atoms that are not oxygen and hydrogen, in the cases where oxygen and hydrogen are not participating directly in the redox process. Then we balance oxygen by adding waters and balance hydrogens by adding protons. Finally, we balance the charge And we want the charge on each side of the reaction to be the same. It doesn't have to be zero, but it needs to be the same for the reactants and the products. And in general, we find that we'll be adding electrons to the left side of a reduction half reaction and to the right side of an oxidation half reaction. Then we're going to combine these two, but before we do that, we have to multiply each half reaction by an integer such that the number of electrons gained in the reduction half reaction is equal to the number of electrons lost in the oxidation half reaction. Finally, we add the balanced half reactions, including phases, and cancel any excess species. We can use as an example the reaction of bromate with hydrazine to produce molecular bromine and nitrogen gas. First, we'll divide this into two half reactions. We see that bromate going to bromine is a reduction process, and hydrazine going to nitrogen gas is our oxidation process. Next, we balance the atoms and charges in each half reaction. So for our bromate half reaction, we balance the bromines by putting a 2 in front of the bromate. Then we balance the oxygen atoms by adding water molecules to the product side such that we have 6 oxygen atoms on each side. Next, we need to balance the hydrogens, and we do this by adding 12 protons to the reactant side such that we have 12 hydrogens on each side of the reaction. Finally, we balance our charges. Before we add the electrons, we see that our reactant side has a total of a plus 10 charge, and our product has 0 charge. In order to make these equal by adding negatives, we have to add 10 negatives to the reactant side. So we add our 10 electrons, and we see that we have 0 charge on the reactant side and product side. You can also see from the oxidation number that bromine goes from a plus 5 state to a 0 oxidation state. And so with 2 bromine atoms, we'll need 10 electrons to accomplish this. Now we can look at the hydrazine half reaction. In balancing the atoms besides oxygen and hydrogen, well, that's already done because there are 2 nitrogen atoms on each side. We don't need to balance the oxygen atoms because there are none to begin with. And then we can balance the hydrogen atoms by adding 4 protons to the product side such that we have 4 hydrogens on each side. Finally, we'll balance up the charge by adding 4 electrons. So now we have 0 charge on each side of the reaction. Next, we multiply each of our half reactions such that the number of electrons lost in one half reaction equals the number of electrons gained in the other half reaction. 4 electrons are lost in oxidation and 10 electrons are gained in reduction. So we'll multiply the oxidation by 5 and the reduction by 2. So by doing this, we see that we have the following result. We have 20 electrons on each side, which can be canceled. We have excess hydrogens, so we have 24 on the reactant and 20 on the product side, so we can cancel the extras. And we end up finally with our 4 protons plus 4 bromates plus 5 hydrazines, giving us 2 moles of molecular bromine, 12 moles of water, and 5 moles of nitrogen gas. This was done in acidic solution. In general, we may have reactions that occur in basic solution. Acidic solution contains protons and waters, so the protons are balancing the hydrogen atoms. Basic solutions will have excess hydroxide ions along with the water. And in order to balance the hydrogen atoms, we need to balance all of the acidic protons, so we add hydroxide to both sides of the equation for every proton that is present. And then we combine any hydroxide and protons that appear on the same side of the equation, and we'll produce water with that. And then the excess water molecules are canceled. You can do practice problems to illustrate this to yourself. Next, we're going to build on this, and we're going to look at electrochemical cells. An electrochemical cell is a system that incorporates two redox half reactions that are physically separated from one another. And we use these to produce electrical energy, or we can use electrochemical energy or electrical energy to drive an electrochemical process that is non-spontaneous. So we have two types of electrochemical cells. First, we have what's called a voltaic or a galvanic cell, and that is a spontaneous redox reaction, one, as you know, that has a delta G that is negative, and it's used to generate electrical energy. The voltaic cell does work on the surroundings. The electrolytic cell uses electrical energy from an external source to drive a non-spontaneous reaction, one which has a positive delta G. In this case, the surroundings are doing work on the system, that is, the system being the electrolytic cell. Both types of cells use two electrodes, and these two electrodes are placed in the two half reaction solutions, the electrolyte solutions. The anode is the electrode is where oxidation occurs, so that's an ox. And the cathode is the electrode at which the reduction occurs. So you just think red cat, reduction cathode. Here we have illustrations of each type of cell. On the left, we have a voltaic cell. Energy is released from the spontaneous redox reaction. The system does work on the surroundings. Here it's listed as a load, so the load is something that you're driving. It could be a stereo. It could be driving a motor, a battery driving a motor, or your battery connecting to the starter in your car. Here, the anode, where the oxidation occurs, produces electrons that run through the load to the cathode, where the reduction occurs. We'll see here that the anode for the voltaic cell is negatively charged. The cathode is positively charged. The oxidation half reaction, we see that a species here is being oxidized and giving us electrons. So those electrons are produced and go into that electrode and then run through the load. The reduction half reaction, the electrons are picked up by the excess Y species in solution, Y plus species, to produce our Y. And we see our overall cell reaction with a delta G that is negative. That's an voltaic cell. That's a voltaic or a galvanic cell. The electrolytic cell on the right-hand side here is where energy is absorbed or some sort of power source is used to drive a non-spontaneous redox reaction. The surroundings is the power supply, and they do work on the system, which is the electrochemical cell. Here, the electrons are forced through the cathode, so the cathode is now negatively charged, where reduction is occurring, and then electrons are pulled from the anode, where the oxidation is occurring. Again, we have the oxidation here being A minus going to A plus an electron, and the reduction is E minus plus B plus goes to B. And our overall cell reaction is shown with the positive delta G being non-spontaneous. So voltaic or galvanic is a spontaneous process. Electrolytic is the non-spontaneous process. Let's take a look at a spontaneous redox reaction. This is one that we might look at back in Chapter 4. So back in General Chemistry 1, we might take a strip of zinc metal and put it in a solution of copper 2. And if we do that and let it sit there, we'll see that the copper will spontaneously reduce to form copper metal, and the zinc will spontaneously oxidize to produce zinc 2, such that the solution will become less blue because the copper 2 hydrated complex is blue. So the solution loses some color, and we see that copper metal will plate out onto the zinc surface. Zinc is oxidized and loses electrons to copper 2, and then the copper 2 picks up electrons and is reduced. What we can do to create an electrochemical cell is by take these two half reactions and physically separate them. So we can take the zinc and a little bit of zinc solution, like a zinc nitrate solution, and put it in one beaker. Here in this figure on the left-hand side, we see it's or on the right-hand side, we see a figure, and in the left part of that figure, we have the zinc half reaction, where we have zinc metal in contact with zinc solution. And our other half reaction, our reduction half reaction, is shown in the right-hand beaker with copper in solution with copper metal piece immersed in that solution. Now we have to have a complete circuit, so we'll have our voltmeter or our load shown on top where the electrons flow through, but we also have to have what we call a salt bridge, or some way of counterbalancing the charge in this such that the circuit is complete. Without the salt bridge, the circuit shuts off. Each half reaction takes place in its own what we call half cell. So these reactions are physically separated. We have the zinc half cell and the copper half cell. Each half cell consists of an electrode in an electrolyte solution. The half cells then are connected by the external circuit and the salt bridge. So if you look closely, the zinc half reaction and the copper half reactions are the same as we saw on the previous slide. The overall cell reaction is the same as the reaction on the previous slide, but we've simply separated the two cells and run the electrons through an external circuit and used that negative delta G to do work. So we can look at the operation of this voltaic or galvanic cell. The oxidation, that is the loss of electrons, occurs at the anode, which is the source of electrons. The zinc goes to zinc 2 plus 2 electrons. And since the zinc is dissolving, over time the zinc anode will decrease in mass and the zinc 2 concentration in solution will increase. The reduction, that is the gain of electrons, occurs at the cathode, where the electrons are used up or consumed. So our copper in solution then consumes those electrons to produce copper. Over time, the copper in solution in the half cell decreases, the blue color fades, and the mass of the copper increases. So you can see here in the lower figure, we've got our zinc electrode. The silver-looking electrode has shrunk in size, and the copper electrode has grown with protrusions building up where the copper has been reduced on the surface. Next, let's look at the charges of the electrodes. And it will vary from voltaic or galvanic cells to electrolytic cells, as we'll see later on in this video. So here, our zinc reacts with copper ions to produce zinc ions plus copper metal. The anode, this is where we produce electrons by the oxidation of the zinc. So oxidation at the anode. The anode is the negative electrode in the voltaic cell because the electrons are being released by the zinc metal. Electrons flow through the external wire from the anode to the cathode, and at the cathode, those electrons are picked up by the copper 2 ions, where the copper 2 then is reduced to copper metal. So the cathode has a positive charge on it. It is a positive electrode in a voltaic cell. Now, the last thing we're going to look at is this salt bridge. That is the thing that completes the electric circuit. This works by allowing ions to flow through both half cells to keep charge neutral, overall charge neutral on each half cell. It contains non-reactive cations and anions, and very often this is sodium sulfate that's dissolved in a gel. And so when the zinc is oxidized at the anode, the zinc 2 ions are formed and enter solution. And of course, on the other half reaction, copper 2 ions leave solution to be reduced at the cathode. So the way we achieve electrical neutrality on the zinc side is that we have to account for that zinc positive charge. The sulfate will move from the inside the salt bridge into solution to counterbalance the zinc charge. And on the copper side, the sodium ions will move from the salt bridge into the electrolyte solution to counterbalance the loss of the positively charged copper ions. So we'll actually have 2 sodium ions for each copper that is reduced. For the sulfate case, we just have a 1-to-1 ratio of sulfate to zinc. And looking overall, electrons flow through the wire from the anode to the cathode. The cations move left to right through the salt bridge into the cathode half cell. The anions move right to left through the salt bridge into the anode half cell. In general, following convention, a voltaic cell is shown with the anode on the left and the cathode on the right. In the previous system, our electrodes were a piece of zinc metal and a piece of copper metal. These are what are called active electrodes. An active electrode is one that is an active component in the half cell and a reactant or product in the overall reaction. In other words, it's either oxidized or reduced, whether it's at the anode or the cathode. There are some species, though, which are in the oxidized and reduced form in solution. In order to allow electrons to be transferred out of the solution, we use what we call an inactive electrode. An inactive electrode provides a surface for the reaction that does not participate actively in the overall redox reaction. Inactive electrodes are necessary when none of the reactants can be used as an electrode. So an obvious example would be when, for our zinc plus hydrochloric acid case, if we have protons, that is our oxidizing agent, which gets reduced down to hydrogen gas, we can't make an electrode out of acid or out of gas. The inactive electrodes that we typically use are graphite or platinum, which are both relatively inert substances. They can sit in solution and they can pick up or release electrons to solution without themselves participating in the reaction. Here is a voltaic cell that uses inactive electrodes. On the top, we have our electrochemical cell, our voltaic cell. On the left-hand side, we have our anode where oxidation occurs. Here, iodide is being oxidized to iodine. So I minus is converted into I2. These two species, we can't make an electrode out of them. And then we have our reduction at the cathode. In this case, permanganate, MnO4 minus, is being reduced to manganese ion, Mn2 plus, so the manganese 2 ion. And in this case, then we have carbon, a piece of carbon as our electrode in both cases. So we use a piece of graphite immersed in each of these electrolytic solutions. So we can carry out our oxidation half reaction, which will produce electrons, which move from the left through the voltmeter to the right-hand side, where they go into the cathode, and the cathode then is where we see permanganate reduced down to manganese 2 ion. And our overall cell reaction is shown here. We could actually do this in a single solution, but if we want to do this to run electricity through an external circuit, we need to separate them into half cells. We have a specific notation because, of course, we could draw electrochemical cells, but that would require on our artwork, which is always somewhat challenging. So we have a standard nomenclature or standard diagrams that we use to illustrate how electrochemical cells work and what the phase boundaries are. And so typically we have the anode written on the left, and we draw a single line for every phase boundary that occurs in the solution. And then the cathode is on the right-hand side. in our zinc copper case, the zinc was the anode. So zinc is being oxidized in the voltaic cell. So we'll have zinc solid with one vertical line. And then we'll have a zinc solution. Very often we'll put the concentration of the solution there. The double line in the center represents the salt bridge. So the first line on the left represents the zinc solution to salt bridge phase boundary. And the right-hand line of that double line represents the salt bridge to the copper aqueous solution phase boundary. Then we have one more vertical line as we go from the copper solution to copper solid. We put our phases for every species, and we often put concentrations in parentheses. So here we have a notation for a voltaic cell that uses an inactive electrode. This is for the iodine, iodide, and permanganate manganese 2 reaction that we just saw 2 slides ago. In that case, we used carbon or graphite as our electrode. So here we have our oxidation on our left-hand side. We have graphite, a line for the phase boundary to iodide, and then a line for the phase boundary to the iodine solid, which is the product. Now, if we had produced something else, for example, I3 minus as our product, we would not put a line, we would put a comma there because there'd be no phase. They would both be in solution. But here we see that iodide and iodine are 2 different phases, one being aqueous solution and one being solid. So we put a vertical line between them. Then we have our 2 vertical lines for the salt bridge. Then we have the permanganate acid and the manganese 2. And notice they're all in aqueous solution, so we have no vertical line. We simply have commas between each because they're intermingled. And then we have one vertical line for our second graphite electrode. We've been looking at voltaic or galvanic cells. Electrolytic cells are ones that involve non-spontaneous redox reactions, which are driven by an external power source. So an electrolytic cell uses electrical energy from an external source to drive a non-spontaneous redox reaction. Let's look at one of these. Imagine we take copper and we have that as our anode. So copper will be oxidizing to copper 2 plus some electrons. So it's acting as the reducing agent now. It is being oxidized. And our other half cell will be the tin 2 ion being reduced to tin metal. If we take these 2 half reactions and add them together, we get an overall cell voltage which is negative, and as we'll see this, not in this video, but our next video, this corresponds to a positive delta G value of 93 kilojoules for the reaction as written. That positive value means this is a non-spontaneous reaction. Now, as with the voltaic cell, oxidation still occurs at the anode and reduction takes place at the cathode. But in this case, an external source supplies the cathode with electrons, which is now negatively charged, and removes them from the anode, which is positively charged. So we see here the tin-copper reaction, and we can contrast the voltaic cell on the left-hand side with the electrolytic cell on the right-hand side. So we're looking at the same reactions, we're just making the electrons move in one direction or the other. On the left-hand side, that is the voltaic cell, electrons spontaneously move from tin to copper, such that copper is reduced spontaneously and tin is oxidized spontaneously. And that would, if you remember back to your activity series, you know that copper was at the very bottom, so that tends to be a species that is readily reduced. So on the left-hand side for our voltaic cell, tin is oxidized, copper is reduced, and our overall cell reaction is shown at the bottom. In this case, the electrons move through a voltmeter, or they could move through your stereo, or they could move through your cell phone or some other electrical device and do work, allow you to hear things or talk. On the right-hand side, we have the electrolytic cell. So now what we're going to do is we're going to make copper oxidize and force tin to get reduced. So what we do is we simply apply a voltage that is greater than 0.48 volts, which turns out to be the cell voltage for this system. And if we apply that voltage and force the electrons in the opposite direction, now the cathode gets a negative charge because the electrons are being dumped onto it. And at that point, then this tin is attracted to those negative charges and gets reduced. And on the anode side, where the oxidation occurs, we've pulled electrons away, therefore the copper metal will pop off the surface and get oxidized. And for our reactions, we simply reverse what we had for the voltaic cell. Our oxidation reaction now becomes the reduction reaction, and the reduction reaction becomes oxidation. Overall, we've simply reversed the overall electrochemical reaction. Comparing the voltaic and electrolytic cells, we see that for the voltaic cells, delta G is negative, E for our cell will be positive, which we'll go through in more detail in our next video. The anode is where we have oxidation, and that is a negatively charged electrode. The cathode is where we have reduction, and that's the positively charged electrode. In contrast, for our electrolytic cell, delta G is positive. It's non-spontaneous. So E cell then becomes negative. The anode still has oxidation, but now the anode is positively charged. The anode is positively charged while the cathode becomes negatively charged for our electrolytic cell. Next, we can look at the electric potential. When the switch is closed and no reaction occurs, well, before a reaction is occurring, if we let the reaction go in an equilibrium state, we can look at our zinc and our copper reactions. So zinc can go to zinc 2 plus electrons, and copper can go to copper 2 plus electrons. Thinking back to chapter 4, we know that zinc is a stronger reducing agent than copper is. Zinc is more readily oxidized than copper is. So the position of the zinc equilibrium lies more towards the right than does the copper equilibrium. We would say that zinc has a higher electrical potential than copper. When the switch is closed, then, electrons will flow from zinc to copper to equalize the difference in these electrical potentials. The spontaneous reaction occurs as a result of the different abilities of the metals to give up their electrons. That is, their differences in reduction potential. So zinc is a better reducing agent, and correspondingly, copper 2 ion is the better oxidizing agent. You would remember that from the activity series you saw in chapter 4. So a voltaic cell converts delta G into kinetic energy of electrons. The cell potential of a voltaic cell depends on the difference in electric potentials between the two half reactions, or the two electrodes in each of the half reactions. The cell potential is the voltage of the cell. Sometimes this is called the EMF, or the electromotive force. You may have heard that term before. The E cell is positive, or greater than 0, for a spontaneous reaction. Remember, delta G is negative for a spontaneous reaction, but E cell is positive, and we'll show an equation for this in our next video. The more positive E cell is, the more work the cell can do, and the farther the reaction proceeds to the right. E cell is negative, less than 0, for a non-spontaneous cell reaction, one for which delta G is positive. That would be an electrolytic cell. Now, if E cell is 0, This is like when delta G is 0, the reaction's equilibrium, the cell can't do any more work, the system's at equilibrium. Here are some voltages for some typical voltaic cells. So common alkaline flashlight batteries are typically 1.5 volts. A lead acid car battery has individual cells, electrochemical cells, with a voltage of approximately 2.1 volts, but they're stacked 6 cells in series such that your car battery has a voltage of around 12 volts. Your calculator battery, and if it's a mercury battery, would have a voltage of 1.3 volts. Lithium-ion laptop batteries around 3.7 volts. Electric eels have a series of 5,000 cells, each with an acting as an electrochemical cell. And a 6-foot eel will typically put out 750 volts of blast if it wants to shock you. But each of its individual cells would have a voltage of about 1/10 of a volt. The nerve of a giant squid across the cell membranes about 0.07 volts. When we want to measure this, we simply use a voltmeter, which you may have used before in a physics course or maybe around your house for testing purposes. So the standard cell potential is what we call E0 sub-cell. And that's measured at a particular temperature with no current flowing and all the components in their standard states. That tells us what the E0 for the system is. So the standard electrode potential for a cell is the potential of a given half reaction when all the components are in their standard states, which we've discussed before. And by convention, all standard electrode potentials refer to the half reactions written as reductions. So we write both the cathode and the anode as a reduction. But then when we want to get the overall cell potential, we take the cathode standard cell potential or half cell potential, and then we subtract off the anode cell potential. The anode cell potential, of course, is where oxidation occurs, but we've written it as a reduction, so we subtract that value off. Now, we have to have a standard upon which we base everything. You can't have a half cell working by itself. A half cell alone will not give you a voltage. If we could measure one, then we would have an absolute measure, but we can't do that. So just as we have for enthalpies and for free energies for that matter, we have a standard. And so the standard we use is the standard hydrogen electrode. And all electrochemical cells are measured relative to the standard hydrogen electrode to get their standard values. So all half cell potentials are measured relative to the standard hydrogen electrode. And we give the standard hydrogen electrode a voltage of 0 as our starting place. What is the standard hydrogen electrode? Well, of course, that's everything at its normal standard state. We have 2 species, the protons and hydrogen, which can't act as an electrode itself. So we need a piece of platinum metal as the electrode. It's an inactive electrode. It's in contact with hydrogen gas, and the pressure of that hydrogen gas is 1 bar. Silverberg says it's atmospheres, which is incorrect. The standard hydrogen electrode is 1 bar bubbling through a solution, and then the platinum electrode is immersed in 1 molar strong acid. So the pH in that case is 0. This is our standard hydrogen electrode and gives us our reference voltage of 0. Here then we could take, for example, our standard hydrogen electrode versus zinc. In this case, we have an electrochemical cell in the center. On the left-hand side is our zinc, which will act as our anode, which is where our oxidation occurs. And then the standard hydrogen electrode spontaneously will be on the right-hand side as the cathode. That's where our reduction will occur. So you can see that the zinc metal is dissolved and lost in solution where oxidation occurs, and then the hydrogen gas, which is continuously passing through, will be augmented by more hydrogen where the acid is reduced to H2. If we measure the voltage on this system, this allows us to know what the standard reduction potential for zinc is. The standard reduction potential will be minus 0.76 volts.